Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to continue our discussions on spatial kinetics of rigid bodies. We will discuss some problems based on the equations of motion that we have developed in the previous lecture. We will start with this problem of an aircraft landing gear taken from the book of Merriam and Craig. An aircraft landing gear viewed from the front is being retracted immediately after takeoff with theta increasing at a rate of 30 degree per second, and the wheel is spinning at the rate corresponding to the takeoff speed of 200 km per hour. The 45 kilogram wheel has a radius of gyration about its z axis of 370 millimeter. Neglect the thickness of the wheel and calculate the angular momentum of the wheel about g and about A. These points are marked. G is the center of mass of the wheel, it is marked by that red dot. The origin of the x y z coordinate system is at G. A is another point on that arm which is retracting the wheel. The diameter of the wheel and other dimensions are specified, and theta is measured from the vertical or for this retracting arm. Let us look at the process by which we are going to approach this problem. We are going to use this x y z coordinate system which is fixed to the arm, but not with the wheel. Therefore, wheel is rotating, the spin of the wheel is observed by an observer sitting at the origin of this coordinate system or who is fixed to this coordinate system. The arm is retracting at an angular rate capital omega that I have marked in the figure, and I am going to represent all these vectors in the x y z coordinate system. Capital omega vector, which is a retraction speed, is minus theta dot j cap. Why minus theta dot? Because when theta is increasing, that means theta dot is positive, it is in the direction of negative y axis. Y axis, if you note the x and z, then you know that y axis is perpendicular to the plane of the screen and coming out of it. Therefore, when capital omega, when it retracts, capital omega is minus theta dot j cap, and theta dot is given as pi by 6 radian per second. It is 30 degree per second, which turns out to be pi by 6 radian per second. All angles must be represented in radian. The spin of the wheel will be represented by this vector p. Now, the aircraft is coming towards us, this wheel is coming towards us, and if you think about it, the wheel is rotating in the direction that I have marked. It is in the negative z axis direction, so negative k cap direction. Therefore, the spin of the wheel is minus p k cap, and p can be determined from the takeoff speed, which is 200 km per hour, 500 by 9 is meter per second, and radius of the wheel is 0.46 meter, the diameter is 920 millimeter, and that gives us the spin of the wheel as 120.77 radian per second. Now, we have everything to write down the angular velocity of the wheel. The net angular velocity of the wheel is the angular velocity of the frame plus the angular velocity of the wheel with respect to the frame, which is nothing but the spin angular velocity. Therefore, capital omega vector plus p vector, and we have all these expressions. I have written this in a column vector form. Now, angular momentum about g, to calculate angular momentum about g, I need the moment of inertia tensor about g. This wheel is to be considered as a thin disk, and for a disk you know that the moment of inertia about the z axis is 1/2 mr square, and in terms of the radius of gyration we write m k square. K is the radius of gyration which is specified. Now, to determine the moments of inertia about x and y, we first considered that this is a thin disk and we use the perpendicular axis theorem. Which states that I x x plus I y y must be equal to I z z, and because this is a uniform symmetric disk, therefore, I x x must be equal to I y y, and that gives us I x x is equals to I y y is equals to I z z by 2, and that turns out to be half m k square. So, m k square, this is half m r square, or yeah. So, m k square, half m k square. I z z is m k square, and this is 1/2 of I z z, therefore, half m k square, or in terms of the radius it is 1/4 m r square. But here, since the radius of gyration is given, therefore, we are using the radius of gyration, and that is how I have populated the moment of inertia tensor. Rest of the terms are all 0, because x y z is the principal coordinates for this body. Okay, we have the moment of inertia tensor, and we need to find out the angular momentum about g. That is straightforward. You multiply the moment of inertia tensor with the angular velocity of the wheel, and that gives us this expression, which on simplification leads us to this value of this is the vector representation of the angular momentum of the wheel about the center of mass. We proceed now to find out the angular momentum about A. Now, A is another point, an arbitrary point. We can have two definitions of angular momentum about A, the absolute and the relative, H A absolute and H A relative. Absolute we do not write, so H A is, we use the expression of shift of angular momentum from the center of mass to the point A. I have written it out, H A is equal to H G plus the vector A G cross the linear momentum of the center of mass. The vector A G is known completely. We have therefore the angular momentum about the center of mass, which is already calculated in the previous step. We have to just add to it the contribution to the angular momentum because of the velocity of or linear momentum of the center of mass about, so moment of linear momentum of the center of mass about A, that is the additional term, and this we have discussed. What is velocity of g? I have to now find out velocity of the center of mass. I can choose a convenient point, let us say V O, which is on the aircraft. V O plus omega is the angular, capital omega is the angular velocity of the arm, and omega cross O G, that will give us the total velocity of or absolute velocity of the center of mass of the wheel. V O, the aircraft is moving at 200 km per hour towards us, I mean it is coming out of the plane of the screen. Therefore, I represent these things as vectors. 500 by 9 meter per second is the velocity of the aircraft j cap, because it is coming out, and omega vector is minus pi by 6 j cap cross O G vector, and O G vector is O A vector plus A G vector. OG vector is OA vector plus AG vector, of which this OA vector, the OA dimension OA is not specified. Let us see what happens of it. I have taken this cross product and I have found out the velocity of center of mass. So far so good. Now, I plug in these expressions in the angular momentum expression about A, the absolute angular momentum. H g, this first vector, this is H g, and the rest of it is A g, this is A g vector, cross this is mass times velocity of g. And if you notice, OA, which is an unspecified dimension, is in the k cap direction. Right now, after taking the this was in the I cap direction, of course, and after I have taken this cross product with j cap, now it has the direction in k cap. So, after taking the cross product, now it comes with a k cap, and A g is already in the k cap direction. Therefore, this term will not contribute, because k cap cross k cap will go to 0. We make a further step. I simplify and do this calculation, and this is what I get. This is the absolute angular momentum about A of the wheel. Let us try to calculate the relative angular momentum about A. For the relative angular momentum about A, this we have again discussed in our previous lectures. Relative angular momentum about A is h g plus the arm A g cross the relative linear momentum of g with respect to A. Therefore, mass times velocity of g relative to A, and because A and g are both points on the same rigid body, this retracting arm, therefore, I can write this relative velocity of g relative to A as omega of the body, which is capital omega, cross A g. And if I substitute all these expressions, I get this as the relative angular momentum of the wheel about A. So, that completes this problem. Let us move to the next problem. A solid right circular cone of mass m, length b and base radius r. The base radius is this dimension, this is the base radius. This cone spins at an angular rate p about its axis of symmetry. Simultaneously, the bracket and attached shaft axis revolve at a rate omega about the x axis. Determine the angular momentum h o of the cone about the point O and its kinetic energy. This is again a problem from Merriam and Craig's book of dynamics. We have to calculate the angular momentum of this cone about O and the kinetic energy. Again, we will use that shifting result for angular momentum. We will take the coordinate system x, y, z that has been shown already in this figure, and this frame is rotating with the arm, the arm on which the cone is mounted. Now, h o, the angular momentum of the cone about O, is equal to h g, the angular momentum of the cone about g, plus r cross m v g. What is r? Now, here r vector is this one. It is not to be confused with the radius of the cone, but this vector. this is the r vector from OG. Essentially this vector is the vector OG. This is our shifting of the angular momentum. We have to calculate therefore first the angular momentum of the cone about its own center of mass, and then add to it the contribution of moment of the linear momentum of the center of mass about that point O. Hg is nothing but Ig times omega, the net angular velocity of the cone. This is net angular velocity of the cone, and the net angular velocity of the cone is omega I cap plus p, which is the spin, times j cap. That is the net angular velocity of the cone. One is the angular velocity of the frame plus p is the spin. So, therefore, plus the angular spin velocity of the cone. The moment of inertia of a cone, of a right circular cone, about its center of mass is represented by this tensor. It is I mean, because this x y z happens to be the principal axis for the cone, therefore, we have a diagonal Ig matrix. You will notice that this is about y y, this is I y y, which is the axis of symmetry, and I x x and I z z are the same, because this is a symmetric object. Finding out Hg is straightforward. We have to multiply the angular velocity vector with the moment of inertia tensor. In other words, we do this multiplication, we write this as a column matrix omega p 0, and this is the result we have. Then we have to find out velocity of center of mass. Velocity of center of mass can be easily represented as velocity of O plus the vector. So, vector from O to G, velocity of O is 0 of course. So, omega cross O G. You may note that O and G are actually points on this same bracket on which the cone is mounted. Therefore, we have this omega I cap is the contribution because of this cross this vector h k cap minus b by 4 j cap is nothing but O G vector. This is the O G vector. H k cap, in the k cap direction, it is this dimension h, it goes up to here and then like this. So, h k cap plus this dimension is b by 4, from the base of the cone to the center of mass of the cone is b by 4, and it is in the negative y axis direction. That is why we have this negative sign. So, this r vector as I mentioned. Now, r cross mass times velocity of center of mass, that means arm times the linear momentum of the center of mass is given by this expression, and if you plug in now all these values in the expression of h o, the angular momentum about O, this is what you will get. So, I leave it to you to complete the details. Now, the kinetic energy of the cone, this we have discussed before. The kinetic energy can be written as 1/2 omega dot h o when it is moving about a fixed point. So, half omega dot h o is the kinetic energy of the cone, and if you plug in h o and omega, omega is also known, everything is known, you will get this as the expression of kinetic energy. Let us try to redo this kinetic energy calculation in a more direct way. We know that kinetic energy of the cone is kinetic energy of translation of the center of mass plus the kinetic energy of rotation about the center of mass. Let us follow this approach. Vg we have calculated in the previous step, Hg also we have calculated in the previous step. Let me show it quickly. Hg is Ig times omega, omega net angular velocity of the cone we have discussed, omega I cap plus p j cap. Hg is this, it is moment of inertia tensor about g times omega, and velocity of center of mass we have calculated this just now in the previous step. We have to calculate Vg dot Vg, which is the magnitude of Vg square, and this turns out to be omega square h square plus b square by 16. And if you plug in all these expressions in the kinetic energy expression, you get back the same expression as we have derived before. So, we have found the kinetic energy expression in two ways, direct and using the expression for kinetic energy about a fixed point rotation. Let us move over to the third problem. A rectangular uniform thin plate with mass of 3 kilogram is welded at 45-degree angle to a vertical shaft which rotates with an angular velocity of 20 pi radian per second. Determine A, the angular momentum h of the plate about O, O is the geometric center through which the shaft passes, B, the kinetic energy of the plate, and C, the moment acting on the shaft due to the plate. Now, this is an example which is very relevant in when you mount plates or discs on a shaft which will rotate. If there is misalignment, if there is an angular misalignment, then that produces a moment on the shaft, and this shows us how to calculate that moment. Of course, here the misalignment 45 degree is too high, it is by design possibly. Okay, the dimensions of the plate are all given. This is a problem from Merriam and Craig's book. We are given this axis x, capital Y, capital Z. Capital Z is aligned with the axis of the shaft about which the whole system is rotating. But this problem can be solved in a much better way or simpler way by considering this red small x y z frame. Why? Because that capital X Y Z frame is not the principal frame for the body, but the small x y z frame is, and that makes our calculations a little simpler. Let us then start calculating this. We have to calculate the angular momentum about that point O. Therefore, I need the moment of inertia tensor, and for a thin plate you might know from mechanics that this is the moment of inertia tensor. Other terms in this tensor are all 0. I have not written them. Therefore, we have only the principal diagonal, and the angular velocity also I have to represent in this frame x y z. It makes an angle 45 degree with y and z, and that is why it has this expression of omega by root 2 j cap plus k cap. And when I multiply this with the moment of inertia tensor, I get the angular momentum about O. Now, if I want to represent this angular momentum about that capital X Y Z frame, what I do, as we have discussed this before in another problem, what we do is we represent this small I j k I cap j cap k cap, the lowercase I cap j cap k cap in terms of this I cap j cap k cap in terms of the capital I cap j cap k cap, and that is quite straightforward in this situation to do. You can very easily notice that small I cap is same as capital I cap, and j cap and k cap have the corresponding representations that I have written out. Therefore, substituting these expressions of essentially I need this j cap and k cap in here, and if I simplify, I get the angular momentum about O in terms of the j cap, capital J cap and capital K cap unit vectors. So, this is the angular momentum about O. Kinetic energy 1/2 omega times omega dot h O, and in the capital I cap, j cap, k cap frame, you can notice that omega, the angular velocity of the shaft, is in the capital Z direction. Therefore, its representation is very simple, 20 pi capital K cap. Therefore, 1/2 omega dot whatever angular momentum we have found, and that gives us 59.2 joule, that is the kinetic energy of the plate. The third part of the problem is to calculate the moment acting on the shaft because of this plate. Now, this is a very important calculation, a very interesting calculation as well. From practical applications point of view, this gives us the moment that a misaligned plate will generate, the moment that a misaligned plate will generate on a shaft. We will use this capital XYZ frame now, because we have all expressions in the capital XYZ frame, and this capital XYZ frame, remember, is rotating with the plate, it is rotating with the shaft and hence with the plate. Therefore, this Z axis is of course always aligned with the shaft, but x axis is on the plane of the, in the plane of the plate. Actually, the plate has been rotated about the capital X axis. Okay, this is the expression of H naught, which we have just now calculated. Omega is known to us. This is also omega of the frame. Remember, this is also the angular velocity of the frame. The moment on the plate, that is MO, M at O, is the time rate of change of angular momentum of the plate about O, and we follow our prescription of taking time derivative del t of H naught, which is the local derivative as seen by an observer sitting or fixed to the XYZ frame and rotating with it, plus omega frame cross H naught. Omega frame is same as omega of the shaft, therefore, it does not make a difference, and if you plug in these expressions of omega, this is the moment 78.96 I cap Newton meter. This much moment acts on the plate to maintain its configuration. As it rotates, to maintain this bent or 45-degree angled shape or configuration, it requires a moment of 78.96 I cap, which is moment is about the x axis. Now, this is on the plate, therefore, on the shaft it is minus 78.96 I cap Newton meter. So, that is the moment generated about the on the shaft because of this plate aligned like this. Therefore, this moment will try to this will produce a concentrated moment on the shaft. So, with that we complete this problem. To summarize, we have looked at some applications of the equations of motion of kinetics of rigid bodies in 3 dimensions. With that, I will close this lecture.